So let's start with the one that you should be most familiar with, and that is the linear approximation. So I have a problem that we got to solve. The problem is to use the tangent line to estimate the square root of 81.5. You remember those other problems you may have seen in the past? Use the line tangent to estimate the zero of the function. Does that sound familiar? No? Well, we'll take a look at what this means. So hit the light. This is kind of hard to see. So let's take a look at this. So what I've got here is I've got the function the square root of x. Okay, square root of x. And I've got a line that's tangent to the square root of x as well. Okay? Everybody see that? There's a line that's tangent. Okay? Then right in here, it gets so close that you can hardly tell the difference between them. See what I'm saying? There's actually two lines here. I can prove it to you if I take off the blue one, the red one's there. Okay, take off the red one, the blue one's there. But what's going on here is this is the square root function, is the red one. And if I want to find the square root of 81, well, the square root of 81 is actually right here. Okay? The square root of 81 is the y-coordinate for that function. Okay? But the square root of 81 is really easy to do because we know it's 9. But the question is, what's the square root of 81.5? And I want you to be pretty accurate. You'd say, well, I don't know, just using common sense, it's going to be a little bit bigger than 9. Okay? 9.1? I don't know. 81.5, let's see. My graph here would be halfway, it'd be like right in here. Okay? I don't know, is that 9.1? 9.05? I don't know. I want to get there pretty accurately. Well, to find the square root of 81.5 is actually kind of hard to do without a calculator. That's kind of the key. So what these guys over here developed is they said, well, wait a second. Finding the value of a function on a linear equation is super easy. It's just a little bit of multiplying, a little bit of adding or subtracting, and then bam, you got it done. So the point here is that to estimate the square root of a complex number like 81.5, we can just use the tangent line instead. And since if we stay close enough to it, we can use that tangent line to find the equation, to find the answer to what the estimate of the square root. Because look at it, they're so doggone close that, well, we got to be pretty accurate. So let's see how we do. All right, hit the light there. So our goal is to use the tangent line to estimate the square root of 81.5. That's what we're going to do right now. So what we're going to do is we're going to write the equation of the line tangent, and we're going to do it at x equals 81. So 60, 70, 81. We're going to find the tangent line at 81, 9. We're going to draw the line tangent to the function at x equals 81. So let's go do that. So I have my point. It's 81, 9. That's the point that I'm going to use. And then now I just need the slope. Okay, what is the slope of the line tangent to the function square root of x when x equals 81? It's 118, right? It's right there. Okay. What is that slope? Well, okay, stop and think. How do you find the slope of a line tangent to a function at a given point? Find the derivative, then plug in the point, and then you get your answer. So here we go. So if y is equal to the square root of x, the first thing we're going to do is we're going to find the derivative, dy dx. This is one that I really want you to know, like, because you got to do it so many times. So the square root of x is the same as x to the 1/2. And so the derivative of it is 1/2 times x to the negative 1/2, which is the same as 1 over 2 square roots of x. So 1 over 2 square root of x is the derivative of the square root of x. Okay? That's just one that I just want you to know. Okay? All right, so evaluated at x equals 81, so dy dx evaluated at x equals 81 is equal to 1 over 2 times the square root of 81, which is 1 over 2 times 9, which is 1 over 18. So what's the equation of the line tangent? Well, we know this point. We know this is the slope. So therefore, the equation of the line tangent is y minus 9 is equal to 1/18 times x minus 81. That's the equation of the line tangent, and that's the blue graph right there. So all we have to do to use the tangent line to estimate it is take this function and plug in 81.5. Okay, so here we go. So it's y minus 9 is equal to 1/18 times 81.5 minus 81. And then y is equal to 1/18 times 1/2 plus 9. Now, back in the days when they developed this, it was an application of the derivative that we technically can get by without now because we have the use of the calculators. But it still is a great way for you to see that how we can actually do this estimation. So now we just have to figure this math out. And for a long time, you think about it, dividing complex numbers or trying to find the square root of a number accurately was pretty hard. And now we can do it with ease. So 1/2 written as 0.5 can be written as 1 over 2. So this is really 9 and 1/36, 36 I should say. 9 and 1/36. Okay, pull out your calculator. What is 1/36? Now, if I were to be cruel, I would have you divide 1 by 36 without a calculator. But I have set my cruel ways aside.
Just for today.
Just for today. I'm bringing it back on the exam. Okay, 1 divided by 36 plus 9. I got 9.0277 and a whole bunch of sevens. Okay? This is my estimate using the tangent line for the square root of 81.5. Let's find out what the real answer is. So the real answer is the square root of 81.5. And look at how accurate we are. How many decimal places? 1, 2, 3, 4. We're accurate to 4 decimal places. Let's just stop and think about this. Pre-calculator days, this was really cool. It's not as fun now because we can just punch it in our calculator. Okay? But this class isn't about that. It's about thinking about where things come from, because we still need new things, and you guys are the ones we need to make them. Pressure, yeah. So,
What? I said I nominate Lightning. I need sleep.
all right. So, you can do this with any function. If we make up some cockamamie function and we want to evaluate some number at it, and you were asked to just estimate it, well, really all you can do is just find the tangent line to a place that's near it, and then you can use that estimate. Now, stop and think. This tangent line is really only good if I'm near x equals 81. You know what I'm saying? I can't use this tangent line to find the square root of 23. It's not very accurate. Okay? But if I want to find the square root of 23, then I would use an equation which is close to the square root of 25. I'd find the equation of line tangent at x equals 25 and then use that as the estimate. Does that make sense? So the tangent line is good, but as long as you're within you can determine your own tolerance. How accurate you want to be is how far you want to go away from it. Okay, so this is all it is. It's called linear approximation because you're approximating the answer using the linear equation, which is the tangent line. Okay? All right, and there's different examples that you're going to come across. All right, now I want to solve the same problem, but I want to use these things called differentials. Okay? So, let's explain what a differential is and how we can use them. So, we're going to use the same exact principle, same exact problem, I should say, but we're going to solve it in a different way. You're going to actually see how we're going to use similar numbers. Okay? But we're going to use these differentials. All right, so what the heck does that mean? So dy and dx are called differentials. Okay? dy all by itself and dx all by itself is each a differential. Okay? Now remember, we often see these as dy dx, right? I always say dy dx is the derivative of y with respect to x. What I'm now doing is I'm saying that each of these things individually are called differentials. Okay? And the thing about differentials is they're separable. Okay? So differentials a little rusty. Differentials are separable, which means we can separate them. That's how I can take dy and dx, and I can treat them as individual things. Okay? Now, dy means estimated change in y. dy itself goes by another name. When we refer to it as a differential, it's called the estimated change in y, meaning the estimated change in the y value. Okay. dx means change in x. Look at the close difference there. When we use dx, it's the actual change. It's not an estimate. Okay? Y is estimated using dy. This will all come together when I do the thing. So this is the basic vocabulary about differentials. Okay? Now watch this. We're going to solve this problem using differentials. So watch this. It's pretty cool. So y is equal to the square root of x is the function that we're going to use. Okay? So let's find the derivative. dy dx equals 1 over 2 square roots of x, because we already know that. This is the part where it gets fun. dy and dx can be separated from each other. Okay? So watch what I'm going to do here. I've got no colored markers. Get my supply. What'd you do now?
Nothing. I did nothing.
I don't believe you. I'm going to watch. I'm good at that. All right. So watch this. I'm going to separate the differentials by multiplying both sides by dx. This is something we've never seen before. dx and dy are two different things. And so if I multiply both sides by dx, I get this new equation. dy is equal to 1 over 2 square roots of x dx. Now, this is so cool. The way you read this is the estimated change in the y value is equal to 1 over 2 square roots of x times the change in x. Meaning, if I want to find the square root of 81.5, I'm going to use x equals 81 and dx equals 0.5. Meaning, I know the square root of 81. And if I shift over just a little bit by 0.5, I can use that formula to estimate the change in the y. So in order to estimate, we'll write this, everybody should write this down. To estimate the change in y, I'm not going to write it out. So to estimate the change in y, you're going to multiply this 1 over 2 square roots of x times the change in x. And this is going to be 0.5. The x is going to be x equals 81. Okay, so let's actually do it and see what happens. So dy, I should say here, for x equals 81 and dx, that means our change in x, of 0.5, this produces the following. dy is equal to 1 over 2 square roots of 81 multiplied by 0.5. This is where the numbers are going to start to look similar to what we just did. So if I change my x by 0.5, the y is going to change by this much. So look at what happens here. The square root of 9 is, or square root of 81 is 9. So this is our 1/18th times our 0.5. Doesn't that look familiar? That's what we had over there. Okay, what is this answer? Just do this. Just take, well, this is 1/36. And what was that? 0.27 repeating? Okay. 0.02? Okay. Okay. 1 over 36 is equal to this decimal. This is what this is saying. If I change my x by 0.5, my y is going to change by 0.027 repeating. Meaning, the square root of 81 is equal to 9. The square root of 81.5 is equal to 9 plus the 1/36, or 9.02777. And remember, this is an estimate. We're estimating the answer. Yes?
So if your change in y was like a negative number, then you would know that you have to subtract it from...
Yes. Yes. Because it's just going to be the change in it. So if it's minus, you're going to subtract it from that 9. Okay? All right. Well, let's just do a different number, different series of numbers, and see how this would play out. Phew. Jeez. That wasn't very good. Okay, let's do another one. Let's estimate the square root of 36.6. Okay? What? No. Yeah. Yeah, this is 2038. I'm not, don't be mad at me. I am, that's my other room. Yeah. It was Mrs. Rosing, and she calls me every now and then to just ask me like something, And sometimes she'll be like, hey, we're in the middle of pre-calc, and I got a question for you. Just answer this quick. Remember that? Yeah. So she was trying to call somebody else, and she felt really bad, and I felt really bad. Okay. All right. Let's do another one. Let's find the square root of 36.6. Like, how does this work? Okay. Same exact problem. So we know that we're still dealing with the square root of x function. Okay. Still the square root of x. The derivative is still 1 over 2 square roots of x. Okay. And then now we can separate those differentials. By multiplying both sides by dx, I get that the change in y is equal to 1 over 2 square roots of x times dx. Just multiplying both sides by dx. Remember, they're separables. They're be counted as two different things. Now to compute the change in the x, I'm going to use x equals 36. And dx is going to be 0.6. Just the change. So that means my change in the y is going to be 1 over 2 square roots of 36 multiplied by 0.6. Okay, we're running out of time here. I need this. What's 0.6 divided by 12? What'd you get? 0.05. Give me more than that. Is there anything more than that? What's 0.05? Oh. So that's the estimate. Calculator now. So the answer would be 6.05 as my estimate. What is the actual square root of 36.6? 6.0497. Okay. So we estimated it pretty quickly to 2 decimal places. All right. Work on those packets tonight, and you'll have all day tomorrow. Yeah. Don't forget your calculator, though.
Oh, yeah, I'll grab that.